Hydroplaning can mean pleasure, or it can mean trouble. Hydroplaning keeps water skis on top and can lift aircraft tires off the runway. This results in extremely low friction coefficients. Aircraft tests have confirmed that braking effectiveness is generally reduced when operating on even slightly wet runways because of lubrication effects between tire and ground. However, the same aircraft tests show even greater reductions of braking effectiveness in the presence of a deep fluid, in this case slush, and it is under these conditions that tire hydroplaning becomes a serious problem. The NASA Langley Research Center has for some time conducted research on this problem, initially with a small wheel and belt arrangement, but more recently at one of its facilities called the Landing Loads Track. The test carriage at this facility can be catapulted by a water jet to speeds in excess of 100 knots. In this research program, various aircraft landing gears and aircraft tires were mounted on the test carriage and equipped with detailed instrumentation. During these studies of tire behavior, the runway conditions varied from dry to covered with 2 inches of water. The effects of slush depths from 1/2 inch to 2 inches were also investigated. It was substantiated during this research program that on wet runways, partial hydroplaning occurred at the lower speeds, and at a higher speed and under certain repeatable conditions, total hydroplaning developed and wheel rotation stopped completely. On the basis of the research, we can explain this phenomenon and offer a simplified explanation of the physical principles. On a standing tire, the only force acting is the ground reaction caused by the weight or vertical load on the tire. For a rolling tire, the situation is more complex, since ground friction, tire deformation, and tire hysteresis are involved. Let us assume that the tire is rolling freely at a fixed forward speed on a dry runway. A rolling resistance force acts in a direction opposite to the motion of the tire and produces a moment on the tire in the accelerating or spin-up direction. To maintain a constant rolling velocity, this spin-up moment must be opposed by an equal spin-down moment, which is produced by a shift of the vertical ground reaction to a position ahead of the wheel axle centerline. The introduction of deep fluid on the runway complicates the picture further, since additional drag on the tire is produced when the fluid is displaced from the wheel path. Also, as the forward speed is increased, the spray pattern thrown up by the tire changes, and a wedge of fluid penetrates the ground contact region, reducing the ground contact area and producing a hydrodynamic lift force on the tire and a condition of partial hydroplaning. As the forward speed is further increased, the spray becomes flatter, the wedge of fluid penetrates further into the ground contact region, and the hydrodynamic lift force becomes progressively greater until at some high forward speed, the hydrodynamic lift force becomes equal to the vertical load being supported by the tire. At this point, complete separation occurs between the tire and the ground. This is the condition of total hydroplaning. Under this condition, ground frictional forces causing spin-up are reduced, since large shear forces cannot be developed in a fluid, and the predominating spin-down moment tends to stop wheel rotation. With further increases in speed beyond total hydroplaning, a large reduction in fluid drag force develops because the tire rides up out of the fluid and hydroplanes along the fluid surface. Directional stability and braking effectiveness of the tire are therefore progressively reduced through partial hydroplaning conditions and nearly vanish at total hydroplaning speeds. The Federal Aviation Agency has conducted tests of an aircraft in an artificial slush bed, which strikingly demonstrated a loss in directional stability and control due to tire hydroplaning. In this free-rolling test, the airplane entered the slush bed at 120 knots, and a crosswind component of 9 knots induced a yaw, which could not be corrected by the pilot until exit from the slush bed. With regard to braking effectiveness, large reductions were observed on the aircraft and at the track at the higher speeds in deep fluid. When wheel rotation stops under total hydroplaning conditions, the futility of applying brakes is obvious. Not so obvious, however, is the reduced braking effectiveness that exists under partial hydroplaning conditions. Analysis of the results of this research program indicated that, surprisingly, changing the weight carried by the tire appears to have little effect on the speed at which total hydroplaning occurs. As the weight on the tire changes, the footprint area changes, so that the ratio of weight to area remains constant, and this ratio is essentially the tire inflation pressure. It is this pressure which the hydrodynamic lift pressure must equal over the entire footprint area for total hydroplaning to occur. The relation between forward speed and tire inflation pressure, the two major factors involved in tire hydroplaning, was studied in controlled tests at the track. With identical vertical load and fluid depth on the runway, the total hydroplaning velocity, as manifested by a decrease in wheel RPM and a leveling off of fluid drag, was, for a tire pressure of 25 pounds per square inch, about 45 knots. For 50 pounds per square inch, about 63 knots. And for 75 pounds per square inch, about 78 knots. These and other test results indicated that a remarkably simple expression based on classical hydrodynamic lift theory could be used to quite accurately predict the total hydroplaning speed. This expression states that the total hydroplaning velocity in knots is equal to 9 times the square root of the tire inflation pressure as measured in pounds per square inch. The hydroplaning speed calculated by this simple expression agrees well with a number of experimentally observed cases of total tire hydroplaning. These cases, obtained from data available at Langley Research Center, were for a variety of pneumatic tire sizes and inflation pressures. Remember, however, that hydroplaning is a progressive phenomenon, and significant losses in braking and directional control are likely to occur below this speed. Based on this figure, the average automobile would be susceptible to total hydroplaning at a speed of around 50 miles an hour, well within legal speed limits. Typical propeller-driven transport aircraft might encounter this condition at about 72 knots. Typical jet transport aircraft might come under the influence of hydroplaning at speeds of 100 knots. Current heavy jet bombers and carrier-based fighters might reach hydroplaning conditions at 160 knots, owing to the very high tire pressures used. While hydroplaning is a deep fluid phenomenon, the actual depth of fluid required is not well defined and depends on runway characteristics and tire tread design. In tests at the landing loads track, which had a fairly smooth test surface, hydroplaning of smooth tires occurred on a runway covered with water to an average depth of 0.15 of an inch. Although rougher or more uneven surfaces might require a greater average fluid depth for continuous hydroplaning to develop, the hazard does exist of intermittent hydroplaning occurring in large puddles. A fighter nose gear was mounted on the small carriage at the track in order to learn more, through photographs and force measurements, about what happens in the tire-ground contact region for partial and for total hydroplaning. Action of water in the footprint area was recorded by a high-speed camera mounted beneath a glass plate in the runway as the tire passed overhead. In this first run, with the tire moving at a speed below total hydroplaning speed, the darker area of the footprint is the contact area between tire and ground. The lighter area of the footprint is the portion supported by the water. This partial separation between footprint and ground indicates a loss in braking effectiveness and directional stability, even under partial hydroplaning conditions. In this run, with the tire moving at a speed above total hydroplaning speed, the complete absence of a dark contact area indicates complete separation between tire and ground, with the entire footprint area now being supported by the water. These tests indicated that tire tread pattern can influence the hydroplaning speed if the grooves provide escape paths for the fluid trapped between the tire and the ground. Since no such relief is available on a smooth tread, hydroplaning would occur in shallower fluids and at lower speeds. The factors then which affect hydroplaning speed are tire inflation pressure, runway fluid depth, runway surface character, and tire tread pattern. Partial hydroplaning has been shown to cause losses in directional control, reduction in braking coefficients, and partial separation of tire from ground. Total hydroplaning can result in complete separation of tire from ground, a reduction in fluid drag, a change in spray pattern, possible wheel spin down, and further reductions in directional control and braking effectiveness. The loss of braking effectiveness in shallow fluid depths, or the greater loss under tire hydroplaning conditions in the deeper fluids, can result in far longer stopping distances for wet than for dry runways. The hydroplaning speed predicted by the simple relation 9 times the square root of p gives a total hydroplaning speed which is, for nearly all current aircraft, within normal operating speed ranges during takeoff and landing. In order to minimize the adverse effects of tire hydroplaning, landings and takeoffs in excessive crosswinds should be avoided on very wet or flooded runways. Further, when landings must be made on a very wet runway, operational techniques such as minimum touchdown speed, early runway contact, early use of brakes, and where possible, use of spoilers and reverse thrust should be employed to minimize the potential hazards of tire hydroplaning and promote safer operations.